Welcome to this calculus lesson. Today, we're going to solve an improper integral using partial fractions. Let's look at the integral we need to evaluate, the integral from 2 to infinity of 1 divided by the quantity x minus 1 times the quantity x squared plus 1 dx. To evaluate this integral, we'll use partial fraction decomposition. We need to express our fraction as a sum of simpler fractions. The denominator has the factors x minus 1 and x squared plus 1. So we'll express our fraction in the form a over x minus 1 plus the quantity bx plus c over x squared plus 1. To find the values of a, b, and c, we'll multiply both sides by the common denominator. Multiplying both sides by the quantity x minus 1 times the quantity x squared plus 1, we get 1 equals a times the quantity x squared plus 1 plus the quantity bx plus c times the quantity x minus 1. Now, let's expand the right side. We get 1 equals a x squared plus a plus bx squared minus bx plus c x minus c. Collecting like terms, 1 equals the quantity a plus b times x squared plus the quantity negative b plus c times x plus the quantity a minus c. To find the values of a, b, and c, we equate the coefficients on both sides. For the x squared term, a plus b equals 0. For the x term, negative b plus c equals 0. And for the constant term, a minus c equals 1. Let's solve this system of equations. From the first equation, we have b equals negative a. Substituting this into the second equation, negative of negative a plus c equals 0, which simplifies to a plus c equals 0, or c equals negative a. Now, using the third equation and substituting c equals negative a minus negative a equals 1, which gives us 2a equals 1. So a equals 1/2. Now that we know a equals 1/2, let's find b and c. b equals negative a, so b equals negative 1/2. And c equals negative a, so c also equals negative 1/2. Now we can rewrite our integral using these values. The integral becomes the integral from 2 to infinity of the quantity 1/2 over x minus 1 plus the quantity negative 1/2 x minus 1/2 over x squared plus 1 dx. We can simplify this a bit. The integral equals 1/2 times the integral from 2 to infinity of 1 over x minus 1 dx, minus 1/2 times the integral from 2 to infinity of the quantity x plus 1 over x squared plus 1 dx. Now we need to evaluate each integral separately. Let's start with the first integral, 1/2 times the integral from 2 to infinity of 1 over x minus 1 dx. This equals 1/2 times the limit as t approaches infinity of the natural log of the absolute value of x minus 1, evaluated from 2 to t. This gives us 1/2 times the limit as t approaches infinity of the natural log of t minus 1 minus the natural log of 1. As t approaches infinity, this diverges to infinity. Now let's evaluate the second integral. Negative 1/2 times the integral from 2 to infinity of the quantity x plus 1 over x squared plus 1 dx. We can split this into two integrals, negative 1/2 times the integral from 2 to infinity of x over x squared plus 1 dx, minus 1/2 times the integral from 2 to infinity of 1 over x squared plus 1 dx. Let's evaluate these integrals one by one. For the first part, the integral of x over x squared plus 1 equals 1/2 times the natural log of x squared plus 1 plus a constant. For the second part, the integral of 1 over x squared plus 1 equals the arctangent of x plus a constant. So the combined second integral equals negative 1/2 times the limit as t approaches infinity of the quantity, 1/2 times the natural log of t squared plus 1 plus the arctangent of t, minus 1/2 times the natural log of 5 minus the arctangent of 2. As t approaches infinity, the natural log of t squared plus 1 approaches 2 times the natural log of t, and the arctangent of t approaches pi over 2. Now let's combine our results to evaluate the original integral. The original integral is the difference between the first and second integrals. The first integral diverges to infinity, but we need to check if it might cancel with the second integral. Let's write the combined expression with limits. 1/2 times the natural log of t minus 1 minus 1/4 times 2 times the natural log of t minus 1/2 times pi over 2 plus 1/4 times the natural log of 5 plus 1/2 times the arctangent of 2. As t approaches infinity, the natural log of t minus 1 is approximately equal to the natural log of t. So we have 1/2 times the natural log of t minus 1/2 times the natural log of t, which equals 0. So the divergent terms cancel out, and we're left with negative pi over 4 plus 1/4 times the natural log of 5 plus 1/2 times the arctangent of 2. So our final answer is negative pi over 4 plus 1/4 times the natural log of 5 plus 1/2 times the arctangent of 2. We can calculate this numerically to get approximately 0.067. To summarize, we evaluated this improper integral by using partial fraction decomposition, finding the coefficients, integrating each term separately, and then carefully analyzing the behavior at infinity to see that the divergent terms canceled out. Thank you for watching this video on evaluating improper integrals. This problem demonstrates several important calculus techniques: partial fraction decomposition, integration of rational functions, and careful analysis of limits at infinity. Remember, when working with improper integrals, always check whether the integral converges or diverges before proceeding.